Hello everybody, welcome back. So in this video, we're going to wrap up section 1.1 from my proofs book. Last time, we asked a couple questions about perfect coverings of a chessboard. Okay, so a chessboard is an 8x8 grid of squares, but what if you cross off some of the squares and you ask, does a perfect covering exist? Can you find one, or is it impossible to find one? So the first question was, suppose we cross off the top left and bottom left squares of the chessboard. Does a perfect covering then exist? And the answer was yes. You could have one, and we're covering it with dominoes. So that's 2x1 grid of squares. So one domino covers exactly two adjacent squares of the chessboard. Okay. So if you cross off the top left and the bottom left squares, then yes, a perfect covering exists. You just place 3 dominoes in the first column and 4 in each subsequent column. Or, of course, there are literally millions of other options for how to tile that. That's just one of the ways. If you pick any one of those and exhibit it, that is a proof that, that there does indeed exist a perfect covering of that chessboard. Question 2 is, well, what if we only cross off the upper left square? Does a perfect covering exist? And the answer was no. The reason is that crossing off one square leaves 63 remaining squares. 63 is an odd number, and therefore you can't do it. Every domino covers 2 squares, right? So one domino covers 2, 2 dominoes cover 4, 3 cover 6, 4 cover 8, but no integer number of dominoes is going to cover an odd number of squares, and that is the reason that fails. Okay. Now it's time for one of my favorite questions, question number 3. It's really fun. It's really tricky to think about. And the problem is, suppose we cross off the top left and bottom right corners of the chessboard. Now does a tiling exist? Okay. So I would strongly encourage you to spend some time thinking about that before moving on. So go ahead and pause the video and really spend some time, 20 minutes more, trying to figure out whether you think that that chessboard has a perfect covering or not. Afterwards, welcome back. So you might be thinking about the first 2 questions we asked. This first question, we crossed off 2 squares, just like in the question 3 that we're now considering. 2 squares are crossed off. So it feels like we're more in this situation than this situation. But it's a little tricky. I mean, so the second situation said, oh, if you have an odd number of squares, then no perfect covering exists. But we don't have an odd number of squares. So does that mean that a perfect covering must exist? No. No, that doesn't follow. All the odd numbers. So the argument over here says if you have an odd number of squares, then no perfect covering. But it says nothing about the even case. It's not saying if you have an even, then yes, absolutely, there has to be a perfect covering. It's not saying that. It only refers to the odd case. So this explanation is not going to be the explanation for why our new board doesn't have a covering, if it doesn't. If it doesn't, this isn't going to be the reason. It would have to be another reason it doesn't. But maybe it does. Maybe we are in this case. So you might have tried to actually do it, right? One way to prove that there exists something is just to exhibit it, to draw it out, to show where would you put the dominoes to make it work. By the way, that's not the only way to show that something exists in math. There are other ways to do it. There are indirect ways to do it that are quite beautiful. But for now, you might try to just show it, just exhibit it, to actually show where you can put all the tiles, all the dominoes to make it work. And let me show you one attempt. So how would you try? Well, my intuition says that the problem points are in these corners. So probably it's best to start putting dominoes near those X's to sort of fix the problems around the X's. Because in the middle, there's a lot of space. You have a lot of freedom. So my intuition says, okay, let's put a domino right next to the X, maybe this upper left X, and maybe just keep placing dominoes down to cover as much of this first column as possible. And that leaves this square in the corner that needs a domino, right? So we know where the domino would have to be in that lower left. It'd have to be right down there. And we'd probably just, I would continue. And you see we have this extra square left right next to this X. Okay. So now we have both squares next to the X's next to this bottom right X that need to be covered. I would probably start with the one closer to the edge and place 3 there. Okay, now we have 2 more problem points. So we know we have to have a domino in this lower white square. Let's put it there and maybe continue the pattern upward. And this upper right square now just needs to be covered. So you see what's happening here. We're just sort of trying to be as efficient as possible. We're identifying the squares where there are problem points, where we know what we have to do. And doing this sort of just has us cycle around, slowly moving towards the middle. And you might have some hope. You're like, oh yeah, this might work out. But as you see, it doesn't work out. Well, I hope you enjoyed those animations because they took me a long time to make. Please tell your friends so that way, if 1 million people watch this video, then the time will be definitely worth it. If 3 people watch it, 2 of which are my parents, maybe not worth it. So tell your friends. And thanks to Grant Sanderson for the animation engine. The GOAT, go watch his videos. You'll see much better stuff than I can do. Anyways, so we've been talking about this. Does there exist a covering of this chessboard where the upper left and the bottom right squares have been removed? So that's what I'm calling question 3. Does a perfect covering exist? So we just tried one way to do it, and it didn't work out. But maybe there's another way. I encourage you to try out more on your own. Also, by the way, it's always a good idea in math when you're exploring things to try to find a simpler case that you can understand and see if maybe at that point it can generalize to the case that you really care about. So what am I talking about? Well, the 8x8 chessboard is pretty big. Big can have some advantages. You can maybe have some more freedom in the way things work out, but it's also so big it takes a long time to sort of lay down dominoes and try things out and figure out what's wrong and undo things. So I would say start with a smaller chessboard. Maybe start with 1/2 the size, a 4x4. That would be much more manageable. And after, you could even try smaller if you want. Keep in mind that there are some things that are just, if you did 5x5, well, that has an odd number of squares, okay? Whereas 4x4 is an even number of squares. So, you want to try to find a simpler case that captures as much as possible about the general case or whatever case you really want to, the bigger case that you want to think about. Sometimes things are too simple, sometimes they're not. So it's an art to try to do it. But I would say start with the 4x4 board and spend some time trying it out. And what you might discover is that it's not working out. And you might even notice if you have 5 examples written down where it doesn't work out, you might notice something about why in every case it's failing. There's going to be a commonality, a similarity, something that exists in all of your examples for it not working. So pause the video and spend some time doing that, please. Okay, well, hopefully you've been working. If you want a hint, here's a hint. It's actually helpful if it's an actual chessboard, not just a grid. What do I mean by that? Well, something about chessboards is there's color on them, there's paint. So when you're working on your 4x4 board, I would not recommend using a board like this. I recommend using a board like that. That's your hint. Spend some time, see if you can figure it out. Okay, your final hint is an animation. Here it is. Here is a chessboard and some dominoes placed on the chessboard. But imagine the dominoes are transparent. You can see through them. What do you notice? Think about that. Okay, so the important observation there is that whenever you place a domino on a chessboard, it must cover, suppose this is the color scheme, must cover one green square and one tan square. Okay? Because what are the four adjacent squares to a green square? They're all 4 tan. What are the 4 adjacent squares to a tan square? All 4 are green. Okay, so you can only cover one of each whenever you place a domino. Okay, so going back to the animation, that is what it looks like. And why is that important? Well, on our chessboard, which used green and white as the 2 colors, we crossed off 2 green squares. So we do have 62 squares, that's an even number, but 32 of those squares are white, only 30 of them are green. Do you see? So have you placed dominoes? Well, how many dominoes are you going to need? Well, with 62 squares, you'd have to have 31 dominoes. If it's going to work out, 31 dominoes is how many you would need. So but 31 dominoes must cover 31 greens, 31 whites. And we don't have 31 greens and 31 whites. Therefore, it's impossible. So no covering exists on this chessboard. That's the answer. Okay, so let me go ahead and write this out. Okay, so I wrote it out. I'm going to try to remember to start labeling the propositions with the numbering used in the book. That way, if you're kind of cross-referencing, that might be helpful. So this was proposition 1.4. The proposition says that if one crosses out the upper left and bottom right squares of an 8x8 chessboard, the remaining squares cannot be perfectly covered by dominoes. Actually, come to think of it, I think we defined chessboards to be 8x8, so this thing is redundant, but that's fine. Okay, so here is a proof. So written out formally, explaining your logic, and giving the answer that you claim. Okay, so proof. Since the chessboard has 62 remaining squares, and a domino covers 2 adjacent squares, if a covering did exist, it would require, so how many dominoes? Well, take number of squares, divide by 2, 31. So 31 dominoes. Also note that each domino covers exactly 1 green square and 1 white square. Thus, 31 dominoes must cover 31 green squares and 31 white squares. Okay, so we first deduced how many dominoes we would need if it did work out. Then we deduced how many greens and how many white squares would be covered with those dominoes. And then we simply say, oh, but look, that's not the situation we are in. However, note that both squares we crossed off were green, leaving 32 white squares and 30 green squares. Thus, it is impossible to have 31 dominoes cover those 62 squares. Okay, great. Well, in the book, there is also, let me pull it up real fast. I do some sort of discuss it a little bit more, and I have a little algorithmic procedure for like another way to sort of think about it. It's the same at its core, but it's sort of slightly different way to think about it, which sort of emphasizes the point that there are many ways to prove something, and even more ways to express the same idea. You know, if 2 people have the same idea for how to prove something, good chance they're going to differ at least somewhat in how they express it, and that's perfectly fine. Very different than your previous math classes. If 2 people took the same derivative, probably their work is going to be almost identically the same. If you're factoring a quadratic, there are only 2 or 3 possibilities for how to do it. But if it's something like this, there are many possible ways to do it. And then I have a little section on asking questions. I've heard it said once that a good mathematician can answer good questions. A great mathematician can ask good questions. There are a lot of very interesting questions out there in math. And it's pretty interesting to think of, why would someone even ask that question? Some of the most famous conjectures are led by people sort of wondering things and coming up with a question that they would like to answer, but being unable to answer it, and it capturing everyone's attention. So yeah, asking questions is good. So I gave a few more questions you could ask about chessboards and tiling. You should come up with some on your own. So for example, question 1 says, if I remove 2 squares of different colors from an 8x8 chessboard, must the result have a perfect cover? Okay, because remember the first way that question 2 didn't have a perfect cover because there was an odd number of squares. Okay, so in this case we're removing 2, so it's still even. Question 3 didn't have a perfect cover because the squares were the same color. Okay, so now I'm taking that one away. And now I'm basically saying, is that it? Or is it possible that I could pick 1 white and 1 green square, remove them, and it still not work for a third reason? So think about that. Do you think these are the only these are basically the only 2 reasons why a chessboard cannot have a perfect cover when you take away 2 squares? Or is there another, could there be another reason why it doesn't? Okay, so that's the question. If you remove 1 white and 1 green, no matter which ones I choose, 1 of each, is it guaranteed that a perfect cover exists or not? Can you find a white and a green where removing it does not, the result does not have a perfect cover? Okay, great. Okay, that's basically the end of section 1.1. There's one more thing I wanted to say. One sec, let me get it. Okay, so the final thing I wanted to mention is that you might look at these chessboard problems and think to yourself, oh, that's fun or cute or whatever, but it's just a little puzzle. Mathematicians don't actually care about things like this, do they? And I wanted to hopefully change your opinion. If that's your opinion, I hope to change it over the next few minutes. So when I was in high school, I had a very similar impression about math. The math we did in school was kind of boring, to be honest. I've taken algebra, geometry, pre-calc, calc, whatever. And, you'd solve a little problem, and then the teacher would get in front and solve 5 more, variations on the same problem. Things are just slightly different, but otherwise it's the same. And then you'd go home and you have to solve 20 more slight variations on your homework. And then you'd show up for the exam and have to solve 2 more. And that was what math felt like to me. And I was fine with it. I didn't hate math, but I was not excited about math at all. Except when I joined the math club. And the math club, they had these fun little problems that required an insight, an idea to solve, and I loved it. And when I got to college, and started taking proof-based math classes, I discovered that my experience in high school math competitions much more closely mirrored real math, the fuel of real math, proof-based math, than my pre-calculus class did. And that's a good thing. So this idea of having a problem, which requires an insight, requires you to sort of think about the thing from a new angle, that's what it feels like to do real math, proof-based math. Secondly, even the problem itself. Real mathematicians care about tiling problems or perfect coverings. There are real, very important problems that are like that. And remember earlier I mentioned that if you can't solve a problem, solve a simpler case. Well, this could be the simpler case of something else. So we looked at you might have looked at the 4x4 case, done 5 examples, and that helped you solve the 8x8 case. Well, the 8x8 case might help you solve something else. I'm not trying to say the 16x16 case. I just mean like an entirely different problem where instead of using rectangles, you use something else, or instead of being a grid, it's the real plane, R2, or something, right? And there are many ways that you could generalize this basic idea into more abstract settings. In fact, that's a very common thing in math. A lot of math involves taking some sort of structure, like a set with objects of some sort, and these objects and the set have some sort of rules or patterns that they follow. These could be things like the real number line, the set of real numbers, something like that, or maybe functions from R to R, or I don't know. Later on, you're going to see algebraic structures, which sort of generalize the idea of addition, subtraction, multiplication, things like that. Groups, rings, fields, things like that. In combinatorics, you might look at graphs, topologies. So there are lots of structures with rules. And the point of having a structure with rules is that it could be the beginning of many different sort of things. It could represent a boiled down version of matrices or of the real numbers or of, I don't know, some sort of geometry. So that's the idea of abstraction. You start with something that is kind of abstract, and because it can then have many particular realizations. So this is kind of an abstract thing. In some elements of it are kind of abstract that you could potentially generalize them. So the ideas that you learn about parity, even versus oddness, dominoes can only cover an even number of squares, or it covers one square of each color. Those could be generalizable to many more situations. And that's a real power of math, in order to take an idea and say, because we are going to start demanding proofs, which is an explanation for why something is true, you can then ask, well, what else, in what other situations does this same idea apply? What else follows from this one truth? And then you do this, and math just starts going on itself. And I mean, it's beautiful. It's a beautiful thing. So that is the end of section 1.1. Section 1.2 will be much shorter. It's just a single section about sort of naming results and stuff. So next time we'll do that. And then after that, we'll get to sort of the main event of chapter 1, which is called the pigeonhole principle. It's going to allow us to sort of do real proofs using a single principle. And I really like it because you can prove a lot of very interesting things with a single principle. So stay tuned. A lot more fun stuff up ahead. All right, see you next time.